Hello. So this is going to be an unusual video. What happened is I recorded my video and then Zoom failed to convert it. And I was wrestling with it for half an hour. I failed, so I'm going to have to do this again. So therefore, the notes are already pre-written. So today we want to discuss velocity transformation. And the setup is the usual setup that you have frame S and frame S prime. Let's say this is a car, this is a train. An object is moving through space. Okay? It could be a bullet, it could be a bird, it could be something, some kind of an object. I get emails with a confusing language, like an object is moving in its reference. An object is moving in its reference frame or something like that. I'm not sure exactly what that means. An object is just is. Object is doing what it's doing. And you can analyze the object from perspective of different coordinate systems, i.e. different reference frames. Reference frame is just a coordinate system. Mother Nature doesn't care about your coordinate system. You are putting a roadmap on Mother Nature. Mother Nature doesn't care. Now, having said that, you can also analyze something from the perspective of a coordinate system attached to the object itself. And we've been doing that. So when we talk about time dilation, we talk about Alice brushing her teeth. In her own coordinate system attached to her, it takes 2 minutes, but in Bob's coordinate system, from Bob's perspective, it takes 5 minutes. So that's kosher. So if that's what you mean, then it's fine. But I'm not sure, because students often phrase things in ways that are confusing, and it's not clear exactly what they mean. In any case, you have two coordinate systems and an object, and you're observing that object moving with respect to each of the coordinate systems. Let's say if the velocity of the object relative to frame S is u. So today I'm going to use this kind of subscripts to make it clear what is the velocity relative to. It's like training wheels. Okay, so velocity of the object relative to frame S is known. Velocity of frame S prime relative to S is also known. And what we want is we want velocity of the object relative to S prime. Okay. Now this is not highbrow. You know how to do this in conventional physics, right? In conventional physics, you know that U equals U prime plus V. Usual stuff. But where does that come from? That comes from Galilean coordinate transformations, which are incorrect. They're superseded by Lorentz coordinate transformations. So let's also figure out what the velocity transformation is. Okay, so what is U? U is dx-dt. Okay, I'm going to use this. I guess it's a marker or a pencil to guide your eye. U is dx-dt. How do we relate it to the prime frame? Well, on the one hand, we know that dx prime given by this expression. Now, what is gamma? Gamma, remember there's a V inside gamma. Inside gamma, there is a velocity mentioned inside gamma. And sometimes I will use a subscript to indicate what specific velocity. So in this case, it's the V that's mentioned inside gamma. So that's what this kind of notation means. Gamma sub V means that when you put a velocity inside a gamma, it's the V that you're putting inside the gamma. If I could also have gamma sub U. In that case, it would be the U that goes inside gamma. So there's multiple velocities, lots of opportunity for confusion. So we put subscripts. Okay, anyway, so this is the transformation. And the time also transforms, right? So you have the following transformation on the time. Now, what is U prime? The velocity of the bird relative to S prime. Well, it's dx prime over dt prime. That's what we mean by u prime. Okay, and so therefore we substitute dx prime from here. We substitute the dt prime from here, and we just put them in, and then we clean things up. And when we clean things up, so here I'm dividing everything by dt, clean, 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 simplify, simplify, and I arrive at this expression. Now it relates u prime to u, okay? And you can invert it to relate u to u prime. And again, plenty of opportunity for confusion. You might say, well, what's u, what's u prime, what's s prime? I'm so confused. So you just have to pick a convention. Let's say police is chasing someone and they're shooting a bullet or something like that. Okay, so let's say S is the frame of the attached to the ground. S prime is the frame attached to the police. And you are trying to relate the velocity of the bullet relative to the police to the velocity of the bullet relative to the ground. So pick a convention and stick with it. Okay, and then you can use either of these two. So if I put the subscripts back, this would say the velocity of the object relative to frame S is the velocity of the object relative to frame S prime plus velocity of the frame S prime relative to S. So this is just the usual. The numerator is just the Galilean numerator. So this is the Galilean, or 2L, I don't know, numerator. The numerator is the same as before. You already know the regular velocity addition formula. And it gets an update, it gets a denominator. So this is the new update. Notice also how the numerator works. This is why the subscripts are useful. If you want object relative to S, well, here's the mnemonic device. Object relative to S prime plus S prime relative to S. So you can see these indices. It's almost like they cancel. It's called the contraction. They contract and you end up with what you want. Okay, this is why I'm using subscripts to guide you, guide your eye or guide your mind. And then the denominator, this goes here, and boom. In any case, you don't have to memorize formulas, but I'm trying to make a rhyme and rhythm out of these expressions that might look too cumbersome. It's the Galilean stuff divided by the denominator, but even the Galilean stuff, velocity of A relative to B, velocity of A relative to C, plus velocity of C relative to B, the C's cancel and you get what you want. This kind of subscription helps you to not get confused. So a couple of points. First of all, if all velocities are much less than C, so you can see if this is less than C, if this is less than C, then this thing right here is teeny, it's tiny. And if it's tiny, I wanted to cover my screen. The denominator, the whole denominator is approximately 1. It's 1 plus E, 1 plus 0.0001. 1. So you just get back the Galilean transformation. So if U over C and V over C is much less than 1, well, U over C times V over C is much less than 1. You just forget about it. Just get a Galilean transformation. So if all velocities are much, much less than C, boom, you get the regular homemade, kitchen-made velocity addition. Point number 2. If either the U prime or the V is equal to C, you get C back. So for example, if U prime equals C, just try it, just substitute, and you will see that U automatically comes out to be C. So this before this is equal to C prime. So it automatically comes out to be C. In other words, the velocity of light is the same in all frames. If it's c in one frame, it automatically remains c in the other frame. And that's how it's supposed to be. So these velocity transformations know about it. They respect the constancy of the speed of light. Now, let's look at an example. So the outlaws, these are the outlaws. They're trying to escape from the police in their getaway car. And they're moving at 3/4 of the speed of light. Let me make this clearer. So at least I do write something. They're going at 3/4 of the speed of light relative to the ground. By the way, there is absolutely nothing special about the ground, okay? When I say Alice is moving at half the speed of light relative to the ground, and Bob is standing on the ground, it's completely equivalent to saying that Bob is in a spaceship and Alice is moving at half the speed of light relative to Bob's spaceship, okay? It's just that we're so used to standing with our feet on the ground that I give you an example where someone is standing on the ground just so you can visualize it. It's just for visualization. Okay, but there's nothing special about Earth's ground. It could be Mars' ground or ground of Venus. It's just for visualization. Ground is not any special, is not any more special than any other frame. Okay, so as the outlaws escape on their getaway car, it goes at 3/4 c relative to the ground. The police, they're riding on the ground, they fire a bullet. And bullet is trying to catch up to the car. The police is going at half the speed of light relative to the ground, and their bullet is going at 1/3 of the speed of light relative to the police, or relative to the gun, right? The gun fires a bullet at 1/3 c, means that the bullet goes at 1/3 c relative to the gun, which is riding along with the police. What we want to know is we want to know the velocity of the bullet relative to the ground. And then we can compare that with the given speed of the outlaws relative to the ground. Because you see, the speed of the outlaws is given to us relative to the ground. When I said 3/4 c, it means it's relative to the ground. So we want to know whether bullet has the same speed relative to the ground. Then you can make apples to apples comparison. So what we want is we want this. Okay, we want this. Well, classically, you would say, well, speed of the bullet relative to the ground is speed of the bullet relative to the police plus the speed of the police relative to the ground, the velocity addition rule. And you would get 1/3 c plus 1/2 c, which comes out to be 5/6 c, 3/4 c, which is bigger than 3/4 c. So you say, yay, the bullet does catch up to the outlaws according to classical calculation. You know, the classical calculation is not right. So we have to fix it. We have to include this denominator. We have to include this gadget right here. Okay, so the numerator is the same, 1/3 c plus 1/2 c. Bullet moving relative to the police at 1/3 c. Police moving relative to the ground at 1/2 c. All good. And we just have to put all these business into here, into the denominator. And when we do that and clean it up, we find that bullet moves relative to the ground at 5/7 of the speed of light, which if you crank out the numbers, it comes out to be 0.71 c, which is less than 0.75 c, the speed of the outlaws. And so according to the correct calculation, the bullet does not catch up to the outlaws run away. Okay? So this is an example where when speeds involved are becoming comparable to the speed of light, then you do need the proper velocity transformation rules. It's no longer just the addition, it has this ugly looking denominator. Okay, well, oh, interesting. What if I do the analysis from the frame of the police. Okay, so let's see. We know that we know the bullet's velocity relative to the police. And we know the ground's velocity relative to the police. It's minus half c, because the ground is now moving in the opposite direction according to the police. And what we do want to know, we want to know the speed of the outlaws relative to the police. We know the speed of the outlaws relative to the ground, but not relative to the police. So what we want to find the speed of the outlaws relative to the police. Let's do it. The speed of the ground relative to the police is minus half a c. The speed of the outlaws relative to the ground is 3/4 c. Okay, so the outlaws are going that way. Ground is moving back, as seen from the frame of the police. What we want is we want the speed of the outlaws relative to the police. Okay. Let's try to work the magic with our subscript. The speed of the outlaws relative to the police is the speed of the outlaws relative to the ground plus the speed of the ground relative to the police. You see, again, the subscripts, they kind of, these G's kind of cancel. It's not a cancellation in a mathematical sense. It's a cancellation in our bookkeeping sense. And then you just put these things into the denominator, into appropriate slots. Okay, velocity of the outlaws relative to the ground is 3/4 c. Velocity of the ground relative to the police is minus half a c. And then you have the denominator that comes along. You get 2/5 c. 2/5 c. So the speed of outlaws relative to the police is 2/5 c. All right. So that's so that's 0.4. That's 4/10. That's 40% of the speed of light. But the speed of the bullet relative to the police is 30% of the speed of light, 33. It's 1/3 c. So the bullet will not catch up. And the fact that the bullet does not catch up to the outlaws cannot possibly depend on the frame in which you're doing the analysis. Right? When we did the analysis from the frame of the ground, we found that it doesn't catch up. And then when we do the analysis from the frame of the police, we also found that it doesn't catch up. Finally, let's go back to the drawing board. What if you have an object that's moving in both directions? So here's the frame S. Now the fact that it has two coordinates matters, right? So you have X and Y. And frame S prime with its own X prime and Y prime. And there's a meteor streaking across the sky. I'm observing the speed of the velocity of the meteor in my frame S, and I see that it has two components, UX and UY. I want to transfer to the frame S prime. Well, the X component we already discussed, right? So X component is transferred. Yeah, X component has its own life of its own. What about the Y component? Well, you see, we discussed that over interval of time dt, if something has a motion in the vertical direction, that vertical distance, dy, remains the same in both frames. That's true. So dy equals dy prime, but dt is not equal to dt prime, you see? So therefore, the velocity, the vertical component of velocity in frame S prime is dy prime over dt prime. And while dy prime equals to dy, but the element of time is not equal to dt. And so you have this kind of a denominator. And interestingly, you come to a conclusion that the vertical velocity is different in frame S prime because clocks tick at a different rate in frame S prime. Okay, so again, notation, this notation reads the y prime component of velocity in frame S prime. Okay, and then there is a trivial analogous expression for y prime. For u prime z prime, the z prime component of velocity in frame S prime. And again, For the inverse relationship, you just put a minus, you just flip a sign that sits in front of the v. Okay? Okay, I hope I will be able to convert this video. That's another half an hour. Thank you. I'll see you soon.